This is B. Naresh, working as assistant professor in AEC department. And today's topic is problems related to rectified parameters. So in this session, we are going to discuss the problems on a rectified here. So basically we are in the three types of the rectifiers. So one is half wave rectifier, one is full wave rectifier, and last one is bridge rectifier here. So we'll see the problems on all these rectifiers here, and we need to determine some parameters like a DC output voltage and a DC output current, ripple factor, and efficiency of with respect to your given rectifier concepts here. So first we'll see the one problem. So a half wave rectifier having a resistive load of 1000 ohms rectifies and alternating voltage of 325 volts peak value, and the diode has a forward resistance of 100 ohms. Calculate peak, average, and RMS value of current. In that, again, one more parameter is we need to calculate DC power output and AC input power and efficiency of the rectifier. So based on this given statement, we need to find out these parameters like peak, average, and RMS values of current, as well as the DC power output, AC input power, and efficiency of the rectifier. First, we need to identify what are the given specifications here. So here they're given that a resistive load of 1000 ohms means RL is 1000 ohms, and it rectifies an alternating voltage of 325 volts peak value. Then a diode has a forward resistance of 100 ohms means RF is 100 ohms here. So first we need to identify the peak value. So in the first case, we need to identify this one, peak value of current. Peak current means we need to find out the IM value here. So hence, and we know that IM is represented as VM by this RF plus RL, means based on the general formula, I is the ratio of voltage to the resistance. So hence, here it is represented as V means VM and R means based on a given circuit. So in half wave rectifier, we are using only the one diode, hence it contains only one diode forward resistance. It is represented as RF. And they also given that a load resistance, hence we need to consider this RL also here. So here the peak value they given that 325 volts means VM is represented as, in a problem they mentioned that the peak voltage is 325 volts and RF is 100 ohms and RL is 1000 ohms here. So hence, while solving this ratio 325 divided by 100 plus 1000, this is the ohms, then it gives the a 295.45 milliamps here. So this is the peak current. So here the IM value is represented as 295.45 milliamps here. Now again, so if you observe this one, then we need to again calculate this average current. So means average current means your IRMS. We need, so the DC current we need to find out here. Average means we need to find out the DC current, and we know that the DC current is represented as IDC is represented as IM by pi. So just now we observe this peak current where IM is represented as peak current. So hence, just now we observe the peak current, and then we need to substitute this peak current and the pi value. Then with respect to this ratio, we need to identify this average current. This average current is also called as your DC current. So now we can substitute this peak value current. So what is the peak value current? Just now we observed that 295.45 milliamps. So hence the milli is represented as 10 to the power of minus 3 divided by this pi. Just you can solve this ratio, then it gives that 94.04 milliamps here. So this is the DC current or average current of a given of a rectifier here. Now again in the problem, again we need to find out RMS value of currents. So peak means we observe this IM, average means we observe the DC current. Now we are going to calculate this IRMS value. So we need to calculate IRMS value here. So now we know that based on the off-wave rectifier parameters, IRMS is represented as 1 by 2 times of your peak current. So here again this IM is your peak current. So again we observe this IM value. Now you can substitute directly this IM value and then by 2 here. So what is IM value we observe? 295.45 milliamps here. Hence I represented here 295.45 milli is represented as 10 to the power of minus 3 divided by this is 2 is a 2 here. Then it shows the IRMS current or RMS value of current is represented as 147.7 milliamps here. So this is your IRMS. So up to this point, we observe the three current parameters. One is peak current, one is average current that is represented as IDC, one is we observe the IRMS here. And next one, we need to calculate the DC power output. So means we need to calculate the DC power is represented as PDC here. So means generally the power is represented as the product of voltage and the current R. So we can also rewrite this equation. V means your I into your R. Again this I means I. Means we can also write I square into your R here. But here we are going to observe this DC power with respect to your off-wave rectifier. Hence, the current here we need to consider the DC current. Hence, I represent it. This I is replaced with the IDC. Hence, I square DC. R means we need to consider your load resistance here. So, just now we observe this DC current also. Now you can substitute this DC current here. And in a problem, the load resistance is represented as your 1000 ohms here. So just represent those two parameters here, I square DC into your RL. So what is IDC value we observed here? 94.04 into 10 to the power of minus 3 means 94.04 milliamps. So this is IDC value here. 94.04 into 10 to the power of minus 3. This is whole square into, and this is your RL value. So in a problem, they mentioned that RL is the 1000 ohms here. Just solve this one. It gives a DC power here. The DC power here it is represented as 8.845 watts here. So this is the DC power output here. Now again in the problem they again asked the AC input power. So AC input power again is represented as, so AC means we need to calculate across with respect to your transformer here. So we know that the transformer output is also represented as your AC voltage. Hence, we need to consider the AC current or RMS current. So hence, I square RMS. And in the place of resistance, we need to consider the diode resistance as well as your load resistance here. Hence, here I represented as RF plus your RA. So we observe this IRMS value. So what is the value we observed in IRMS here? So the IRMS we observed that 147.7 milliamps this one. So now we are going to substitute this IRMS in a AC input power here. Hence, so here I am going to substitute this IRMS value. So what is IRMS value? 147.7 milliamps here. So this value is IRMS, and that is whole square into, and here I am directly writing RF plus RL, and we know that RF is 100 ohms and RL is 1000 ohms. The total resistance is 1100 ohms. So that is the reason directly I represented this is 1100. So this 1100 is the summation of diode forward resistance and load resistance here. Then simplify this relation, then it shows that the AC input power is represented as 24 watts here. So this is AC input power. Then finally, now we are going to observe the efficiency of a given of a rectifier. So we know that generally the efficiency is represented as it is a ratio of DC output power to the AC input power. So DC output power is represented as PDC, AC input power is represented as your PAC. Just now we got this DC output power as well as your AC input power. Now we need to substitute these two values then to observe this efficiency of the rectifier here. So, and the DC power is 8.84 watts and the AC we observe the 24 watts here. Then you can apply this ratio. If you want to identify the percentage, it should be multiplied with your 100. So if you want to identify the percentage, then we can write this is DC power to the AC power. It should be multiplied with your 100. So here I got this percentage. Now how much percentage you can solve this one? It shows that 36.85%. So this is your efficiency. But again, you need to cross verify that one. In a half-wave rectifier, theoretically, the efficiency is represented as 40.6%. Theoretically, it is represented as 40.6%. So we need to verify practically that should be within the limits of your theoretical value. So here this is practically with respect to your given parameters, we got this efficiency is 36.85%. But theoretically that is related to your 40.6%. So up to this point, we observed with respect to your half-wave rectifier, your peak current and DC current, AC current, DC output power, AC input power and efficiency of your rectifier here. Now we'll see the other problem. So just first read the statement. A half-wave rectifier is used to supply 24 volts DC to a resistive load of 500 ohms and the diode has a forward resistance of 50 ohms. Calculate the maximum value of the AC voltage required at the input here. So in this problem, they mentioned that so a half-wave rectifier is supplied the 24 DC means they given that the VDC is represented as 24 volts and the resistive load means RL is represented as 500 ohms. And again, diode has a forward resistance of 50 ohms. Hence, it is represented as RF is represented as 50 ohms. From this statement, we need to calculate the maximum value of the AC voltage is required at the input side. So based on these given statements, now we need to calculate. So first we need to calculate a load current means average current, that is a DC current. So it is represented generally it is represented as V by R. Means V means which voltage we need to consider here. We are calculating with respect to your DC current. Hence here we need to consider the DC voltage based on a given state. And R means they given the load resistance. So VDC they given that 24 volts and load resistance they given that 500 ohms. Hence here we need to substitute VDC is 24 volts divided by your 500 ohms here. Now what happens here, this ratio gives that 48 milliamperes here. 24 divided by 500, this ratio gives that 48 milliamperes and this is your DC current, IDC value here. Now we need to observe, so the maximum value of load current means we need to identify the peak, and we know that IDC is represented as, in another way, IDC in half-wave rectifier, IDC is represented as Im by pi. So we got this IDC value. Now here we need to calculate this Im value here. So hence, how to write this Im value? Im is represented as IDC times the phi value here. So hence, here I represented this. If you want to calculate the peak current, IM is the representative from this IDC relation. I represented this value from this IDC relation here. Based on the off-wave rectifier analysis, DC current is represented as IM by pi. From this, I am going to calculate this IM value. So hence, IM is equal to pi times your IDC value. So just now we got this IDC value. Just can substitute this IDC value here. So what is IDC value of 48 milliamperes here? So hence pi is a pi. IDC is replaced with 48 milliamperes. So milli means 10 to the power of minus 3. Just solve this product here 5 times this one. Now it produces the peak current is 150.8 milliamperes here. The peak current is represented as 150.8 milliamperes here. So from this, now we are going to calculate how much voltage is required at the input side. So for this case, we are going to find out this VM means input side we require the VM. So V means in terms of generally V is the product of I and your resistance, current and your resistance. So here we are going to calculate the maximum voltage is required at the input side. So that is represented as the peak voltage. Hence we require the peak current. That is the reason. Here I is replaced with your IM. And R means we need to consider along with the internal circuit resistance, means the circuit contains diode as well as your load resistance. So hence diode, when the diode is conducting, it offers a forward resistance. Hence we need to consider a diode forward resistance along with your load resistance here. So just now we observed this IM value and RF they given that 50 ohms. RL in the problem they mentioned that 500 ohms here. So hence we need to substitute all these three parameters here. Then we need to observe how much maximum voltage is required here. So hence, so here IM is represented as 150.8 milliamperes here. So this is your IM. So now this is RF plus RL. So what is the RF? RF they given the 50 ohms and RL they given the 500 ohms. The total resistance is 550 ohm and directly substituted this 550 ohms here. Then can do this product here. 150.8 milliamperes is multiplied with your 550 ohms. Then it produces the voltage is 82.94 volts. So this is the maximum voltage is required at the input side to produce the DC output voltage is 24 volts here. So to produce the DC output voltage 24 volts, the input side, this rectifier requires 82.94 volts here. Now we'll see another problem here. An half-wave rectifier has a load of 3.5 kilo ohms. If the diode resistance and the secondary coil resistance together have a resistance of 800 ohms and the input voltage has a signal voltage, the peak value of 240 volts. Calculate peak, average and RMS value of the current flowing, DC power output, AC power input and efficiency of the rectifier. So in this problem, they mention that the load resistance RL is represented as your 3.5 kilo ohms. Then if the diode resistance as well as the secondary coil resistance means, so in this rectifier we are going to use a transformer. Transformer contains primary winding as well as your secondary winding. So here the secondary coil resistance we are considering here together along with the diode resistance as well as the secondary coil resistance means RS plus your RF, they given that the resistance is 800 ohms here. And the input voltage, I have a signal peak, that is the input voltage peak value is 240 volts. So based on these three parameters, we need to calculate the peak current as well as average current as well as your RMS current. Then after that, we need to calculate a DC power output. After that, we need to calculate AC power input. Then after that, we need to calculate efficiency of your half-wave rectifier. So first we are going to observe what is the peak current with respect to your given this specifications here. So for this case, and we know that the peak current, so generally it is represented as I is represented as V by R. So here this V is replaced with Vm. R means we need to consider the total circuit resistance. Means in a problem they mentioned that together the transformer secondary coil resistance along with the diode resistance, and it also contains a load resistance. So that is the reason where this Rs plus Rf means where Rs is transformer secondary coil resistance, Rf is the diode forward resistance, and RL is load resistance. And in a problem, they mentioned that the together transformer secondary coil along with this diode forward resistance Rs plus Rf they represented as 800 ohms. And in the problem again they mentioned that load resistance is 3.5 kilo ohms here, and the Vm is 240 volts. Now we need to calculate the peak value of current. So just you can substitute these values. Vm is the 240 volts, Rs plus Rf is the 800 ohms, and the load is the 3.5 kilo ohms means 3500 ohms here. Just solve this ratio, it gives that 55.81 milliamperes, that is related to your Im value, means peak value of current for a half wave rectifier. So the peak current is Im is 55.81 milliamperes here. Now we are going to calculate average value of current. So that average value of current is represented as your IDC here. So hence, so we know that the relation is IDC with respect to Im. So we know that the relation is IDC is equal to Im by pi. Just now we got the Im value. Now we can substitute this Im value with respect to this pi. Then we need to observe this DC current here, or average value of current. So your Im value is, we got this 55.81 milliamperes, means where milli means you can substitute this 55.81 into 10 to the power of minus 3 divided by your pi value. This all this ratio, it gives the 17.77 milliamperes here. So this is the DC current or average value of your rectifier here. So IDC is 17.77 milliamperes here. Now we need to calculate RMS value of current, IRMS. So what is the relation between IRMS and Im here? So we know that this relation is IRMS is 1 by 2 times of your Im. So where Im is again your peak current. Now we need to substitute this Im value with respect to this 2 here. So now we can substitute this Im value. So your Im value is 55.81 milliamperes, means 55.81 into 10 to the power of minus 3 divided by 2. So what happens here, this ratio, it gives that 27.9 milliamperes. So this is your IRMS, or the RMS value of current here. So apart from these, all these three currents, now we are going to calculate the DC power output. So generally in a half wave rectifier, the DC power is represented as I square DC into RL here. So means where I square DC means IDC means your average value of DC current. So just now we got this IDC value. Substitute this IDC value with respect to your load resistance here. So in a problem, the load resistance they are given that 3.5 kilo ohms. Now I am going to substitute these values here. So IDC value is 17.77 milliamps. Just now we have got here. Just can check it here. So here this is IDC value. What is IDC value? 17.77 milliamps. So hence I am going to substitute this IDC value here. So here this is IDC value 17.77 into 10 to the power of minus 3. This is whole square into RL means 3.5 kilo ohms. That is nothing but a 3500 ohms here. Just solve this one, then it shows that the DC power is 1.105 watts here. The DC power is 1.105 watts here. Similarly, now we need to calculate AC power input here. So hence, the PAC is represented as we know this relation I square RMS times your RF plus your RL. But actually, in a problem, they mentioned that it contains a together resistance, means transformer secondary coil along with the diode forward. Means from that we need to write the statement, the AC input power. From that representation, we can also read this equation I square RMS into. So we need to write this RS plus RF plus your RL. Now we got this IRMS value and RS plus RL, they given that 800 ohms here. RL is 3.5 kilo ohms. Now we need to substitute all these three parameters to absorb this AC input power here. Now we can substitute these values. IRMS value is 27.905 milliamps. Milli means 10 to the power of minus 3. That is whole square into. So 3500 plus. So this is RS plus RF. They together they given that 800 plus RL means your 3500. So total the resistance is 4300 ohms here. So hence directly I substitute this one 4300 ohms here. So solve this one. Now it shows that 3.348 watts here. So this is AC input power. So from the given specifications, the AC input power of half-wave rectifier is 3.348 watts here. Now by using this DC output power and AC input power, now we are going to determine the efficiency of the half-wave rectifier here. So in generally, we know that the efficiency of the rectifier is defined as it is a ratio of DC output power to the AC input power here. Hence, here I represented this one PDC by PAC. Now, so we got this PDC value and AC power here. DC power we absorbed, AC power absorbed here. Now we need to substitute these two values to absorb this efficiency of a half-wave rectifier here. So if you want to percentage, now you can write this one. DC power to the AC input power is the product of 100 here. And we observed the DC output power is 1.105 watts. And the AC input power just now we observed that is 3.348 watts. That is product with your 100 if you want to identify the percentage. Now this value gives the 33% here. So based on the given specifications in a half-wave rectifier, the efficiency is represented as your 33%. So based on the given all these statements, we observe that peak current, average value of current, RMS value of the current, DC power and AC input power, and we also observe this efficiency of a given problem statement here. Now we'll see another problem here. An half-wave rectifier circuit supplies 100 milliamperes DC to a 250 ohms load. Find the DC output voltage, and PIV means your peak inverse voltage, a rating of a diode, and the RMS voltage for the transformer supplying the rectifier. So here we need to calculate the DC output voltage as well as peak inverse voltage. So we know that in half-wave rectifier, basic analysis of the half-wave rectifier, the peak inverse voltage of half-wave rectifier is only the VM. Then we need to calculate RMS voltage for the transformer here. Now we'll see here one by one. So first we need to calculate the DC output voltage here. So we need to calculate DC output voltage. So the DC output voltage here it is represented as VDC here. So actually the VDC means either that is Vm by pi in half-wave rectifier, or we can also write with respect to given specifications. But here in this problem, they mentioned that this half-wave rectifier circuit supplies 100 milliamperes, means directly they mentioned that DC current. So means we need to write this DC output voltage with respect to this IDC value. Hence, here I am writing this VDC with respect to your given specifications IDC along with your load resistance. V is generally the product of I and your resistance, current and your resistance. Hence, here we are going to calculate this DC output voltage. Hence, we need to consider the DC current along with your load resistance. So in a problem, the DC current is represented as 100 milliamperes here. So means 100 into 10 to the power of minus 3 And the load resistance, they mentioned the 250 ohms here. Then this can solve this product, then it gives the DC output voltage is 25 volts here. Then again, the second one, we need to calculate the maximum value of secondary voltage Vm. And we know that VDC is equal to another representation. The VDC is represented as Vm by pi, one more relation from the analysis of the half-wave rectifier. So by using this relation, we know this VDC value. Now we need to calculate this Vm value. So hence, from this relation, we need to write this Vm is equal to VDC into pi. That is the reason I represented this one. The maximum value of the secondary voltage Vm is represented as the VDC into your pi. So means VDC value we just now we observed, that is the 25 volts. This 25 volts is a product with the pi value. Then it gives that the maximum value of the secondary voltage is 78.54 volts here. Now again, so we need to calculate the peak inverse voltage. So basic analysis of the half-wave rectifier, we know that the peak inverse voltage of a half-wave rectifier is only the V. Means that how much reverse voltage is required without destroying the diode operation in a half-wave rectifier. That is your peak inverse voltage. So based on that analysis, we observed that in a half-wave rectifier, the peak inverse voltage of your rectifier is Vm. So what is the Vm value? Just now we observed that Vm value is 78.54 volts. Hence here also the peak inverse voltage is 78.54 volts here. Now we need to calculate the RMS voltage of the transformer. So in a problem they ask that, so one is DC output voltage, we observe the DC output voltage. One is where they observe the peak inverse voltage. Now another way they ask that RMS voltage of the transformer. So hence, so VDC we observed here, DC output voltage. To identify the peak inverse voltage, first I identify the Vm voltage. That is the reason from that representation, the peak inverse voltage is Vm, that is 78.5 volts. To observe this Vm voltage, I use that relation that VDC is equal to your Vm by pi. So from this, I use this Vm is equal to VDC times your pi. Now I'm going to calculate the RMS voltage of the rectifier. So means we know that in half-wave rectifier, Vrms is represented as Vm by 2. So here Vm is a known parameter. What is the Vm value? Your 78.54 volts divided by 2. That is equal to your 39.27 volts. That is your Vrms voltage of the transformer rectifier voltage, supplying voltage here. So that is 39.27 volts here. Now we'll see another problem. A 230 volts 60 Hz voltage is applied to the primary of a 5:1 step down, center tap transformer used in a full wave rectifier having a load of 900 ohms. If the diode resistance and the secondary coil resistance together has a resistance of 100 ohms. So it depends upon these statements. We need to calculate the DC voltage across the load, DC current flowing through the load, DC power delivered to the load, and the rectification efficiency. So this problem is related to full wave rectifier, and here they are not given the how much voltage is generates across the transformer secondary, but they given that indirectly the transformer turns ratio. The transformer turns ratio is represented as 5:1. But input power for the transformer, the input power is 230 volts. But based on this utilization of this transformer turns ratio, we need to calculate the secondary voltage across the transformer. Then we need to identify this, how much DC voltage is required generates across the load, and how much DC current is flowing through the load, and how much DC power is delivered, and how much efficiency is generates depends upon these statements here. So now first we need to calculate how much voltage is generates across the secondary winding of the transformer with respect to your given turns ratio. So to observe that one, the voltage across the ends of the two secondary winding. So they given that a 5:1 ratio means the primary winding turns are 5, secondary winding turns are your 1. Means the ratio means N2 by N1 times of your input voltage that is generates across the secondary voltage here. So hence, where the secondary winding turns is 1, the primary winding turns is 5, the ratio is N2 by N1 means 1 by 5 times of your input voltage, that is input voltage is 230 volts, and that gives that 46 volts. And this 46 volts is generates across the two ends of the secondary. And but in a full wave rectifier, we are going to use the center tap transform. If you observe the center tap transformer, so it contains one primary winding, but it contains two secondary windings. So this total, the secondary winding voltage is 46 volts. But we need to find out each secondary voltage here. So for this case, here I am going to find out each secondary voltage is a VRMS is actually here is represented as that is 23 volts here. So this is center tap transformer contains the two secondary windings. So across the total secondary voltage is 46 volts. But here I am going to calculate each secondary voltage across the center tap transformer. So means we are on the two secondary winding. That is the reason I made the off here 46 by 2. That is nothing but your 23 volts. So here why I am representing this RMS means, so the transformer output voltage is always your AC voltage. That is nothing but that is the reason. Here I represent it as your RMS voltage. Now, if you want to identify the peak voltage across the transformer secondary winding, so we know the relation. What is the relation here? VRMS is equal to Vm by root 2. So means Vm is equal to root 2 times of your VRMS. So if you want to calculate the peak voltage, now we need to apply this relation here, root 2 times of your VRMS. So what is the VRMS across each secondary winding? Each secondary winding contains 23 volts VRMS here. So by using this VRMS voltage, now we are going to calculate the Vm voltage. So that is the reason. Then the Vm is equal to root 2 times of your VRMS here. So VRMS is 23 volts. Hence Vm is equal to 32.52 volts. This product of root 2 into 23. It gives the 32.52 volts. So up to this point, we got the Vm voltage here. Now I'm going to calculate the DC voltage. In a full wave rectifier, we know that VDC is represented as 2Vm by pi. So hence, the DC voltage here is represented by 2 times of the Vm by pi. So just now we observe the Vm value. 2 into Vm is 32.52 volts divided by your pi value. Then it gives that the ratio is 20.7 volts. So this is VDC value, DC voltage across the rectifier by using this full wave rectifier. Now again we need to calculate the DC current flowing through the load. So hence we know that IDC is represented by VDC divided by. So in a given full wave rectifier, it contains, in a problem they mentioned that transformer secondary resistance together with your diode forward resistance. Hence RS plus RF along with your load resistance. So in a problem they mentioned that the transformer secondary coil along with the forward resistance is 100 ohms and the load resistance is 900 ohms. Means 100 plus 900 ohms, the total resistance is 1000. And the DC voltage, just now we observed this DC voltage. The DC voltage is 20.7 volts divided by this total resistance is 1000 ohms. Then it gives that the DC current is 20.7 milliamperes here. So this is the DC current here. Now again, we need to calculate how much DC power is delivered across the load here. So hence, we need to calculate the PDC at the output side. That is represented as I square DC into your RL. So just now we got this IDC value. What is the IDC value we observed here? IDC value is represented as 20.7 milliamperes. So hence, you can substitute this IDC value here. So IDC value is 20.7 milliamp. Milli means 10 to the power of minus. So this is IDC value to whole square, and RL is 900 ohms. Just solve this product here. 20.7 into 10 to the power of minus 3 whole square into 900. It gives the DC output power, that is 0.386 watts. The PDC value or DC output power is represented as 0.386 watts. Now in a problem, again they ask the rectification efficiency. We know that if you want to calculate the efficiency, it is the ratio of DC output power to the AC input power. So we got the DC output power. Now first we need to calculate AC input power to absorb the efficiency of the full wave rectifier here. So hence, here I am going to calculate the first. So if you want to calculate the AC power, what we require your I square RMS into RS plus RF plus your RL. So first we need to find out this IRMS value here. So that is the reason. So this is the unknown value here based on the given problem statement. We have not identified this IRMS here. To observe this AC input power, first we need to determine this your IRMS current or RMS current here. So we know that in a full wave rectifier, the RMS current is represented as 1 by root 2 times of your IM. So again, IM is also not there, but we know the one relation, IM relation. So that is IM. What is the IM relation? IDC is equal to your IM by pi. That is 2 IM by pi. In a full wave rectifier, the DC current is represented as 2 times of IM by pi. So here we require this IM. So means how to write this one? IDC into pi by your 2. So hence this IM here I am replacing with IDC into pi by 2, and this root 2 is a root 2. So here, and by using this relation, this I substituted here. Now I can substitute these values here. What is IDC value? And then 2 root 2 and this pi value here. So, and we know that the DC current is 20.7 milliamperes. So IDC is 20.7 into 10 to the power of minus 3. This pi is a pi. Again, this is 2 root 2. By solve this ratio, then it gives a 22.9 milliamperes here. So this is IRMS here. By using this IRMS, now we are going to calculate the AC input power here. So hence, now I am going to calculate the AC input power. The AC input power is represented as I square RMS into RF plus RF. But depends upon your problem statement. In a problem, they also mention the transformer secondary coil resistance. Hence, I am going to rewrite this equation. The AC input power is represented as I square RMS into the RS plus RF plus your RL, where RS plus RF is the combination of transformer coil secondary coil resistance along with your diode forward resistance here. And just now we observe this RMS current here. Hence, what is the IRMS value? 22.9 into 10 to the power of minus. It means 22.9 milliamperes. That is whole square. And we know that RS plus RF, they given that 100 ohms, and load resistance they given that 900 ohms. The total resistance is your 1000 ohms. Hence, directly I substituted here. The total resistance is your 1000 ohms. Then you can product these two, 22.9 into 10 to the power of minus 3 whole square into 1000, and it gives the rate AC input power is 0.52 watts here. So up to this point, we got this DC output power and AC input power. Now we are going to determine the efficiency of full wave rectifier here. So what is the formula for efficiency of the rectifier? So it is defined as it is a ratio of DC output power to the AC input power. So hence, so we got this DC output power and AC input power. Just substitute these two values to absorb the efficiency of the full wave rectifier. So for this case, and if you want to identify the percentage, now can this is equal to PDC by PAC into your 100. Now I am going to calculate this percentage. So your DC output power is 0.386 watts and AC input power is 0.52 watts with the product with 100. Then this ratio gives the 74.2% here. And again, we know that in a theoretically, So in a full wave rectifier, the efficiency is 81.2%. That is nearer to your theoretical value. So here, up to this point, we observe that your peak current, RMS current, and DC current and DC output power, AC input power, efficiency with respect to your given full wave rectifier here. So in this session, so we observed some of the important parameters related to your half wave rectifier as well as your full wave rectifier, depends upon your given problem statement D. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.